Children, I hope you have gone through my previous video, and today we will continue further. Children, today in the chapter Coordination Compounds, we are going to study about bonding in coordination compounds. Now, some important properties like geometry, color, magnetic properties of coordination compounds have been explained by the following modern theories, that is the valence bond theory, crystal field theory, ligand field theory, molecular orbital theory. But because of the reduced syllabus for 2021, now only the valence bond theory is in your syllabus this year. Now let us start with the valence bond theory. The main assumptions for valence bond theory are that the central metal ion or atom in the complex makes a number of vacant orbitals available for formation of coordinate bonds with the ligands. The required number of atomic orbitals s, p and d of the metal atom or ion hybridize to give a set of equivalent orbitals of definite geometry. Like for example, if the neighboring atoms are 4, coordination number is 4, hybridization will be sp3. Alright, 1s and 3p will hybridize, and in that case the geometry of the molecule will be tetrahedral. But if coordination number is 4 and the hybridization is dsp2, the inner d, then s and 2p orbitals, then in that case the geometry of molecule becomes square planar. If coordination number is 6 and the hybridization is sp3d2 or d2sp3, in both cases the geometry of the molecule will be octahedral. The d orbitals involved in hybridization can be either inner d orbital, that is n-1d, or outer d orbitals, that is nd. So in d2sp3 this is inner d, and in sp3d2 it is the outer d. Okay. Now each ligand has at least one orbital containing a lone pair of electrons. The empty hybrid orbitals of metal atom or ion overlap with the filled orbitals of ligand to form coordinate bonds. Now during the complex formation, Hund's rule is strictly followed, but under the influence of strong ligand, the electrons may be forced to pair up against the Hund's rule. Now next is application of valence bond theory. We will take it up with a few examples of octahedral complexes. In octahedral complexes, I told you that the coordination number should be 6. Now the octahedral complexes, they are formed by either d2sp3 or sp3d2 hybridization. Then they can be grouped into two categories. First is the inner orbital complexes. Now this complex involves d2sp3 hybridization because participation of inner d orbitals, that is n-1 d orbital of central metal atom or ion, is there during hybridization. In this type of complex, there are lesser number of unpaired electrons or no unpaired electrons because electrons of the metal are forced to pair up. Such a complex is also called as low spin complex. Example of such complexes: FeCN6 3 minus and CONH3 3 plus. Now inner orbital, it uses n-1 d minus orbitals, and that is why it is low spin complex. Now next is the outer orbital complex. Now outer orbital complex is formed by the use of outer d orbitals for hybridization, that is sp3d2. It is called outer orbital complex because we have large number of unpaired electrons, and hence it is also called as high spin complex. For example, FeH2O 3 plus and COF6 3 minus. So outer orbital complex is using outer orbitals, hence it is called as high spin complex. Let us take a few examples to understand this. First is formation of FeCN6 3 minus ion. Now you know that iron has atomic number of 26. So in ground state the electronic configuration is 4s2 3d6. So 5 orbitals of 3d, they are filled with a single electron first, and then the first 3d orbital, it is paired with, the electron is paired with opposite spin. Now Fe3 plus ion, 3 plus means it has lost 3 electrons. So it will lose 2 electrons from the 4s orbital and one from the paired electron in 3d. So it now has 3d5, 4s0 and 4p0. Now it will form coordinate bonds with 6 Cn electrons. So Cn, you know, Cn minus has a lone pair of electron. So 6 Cn minus will donate one lone pair over here like this. See, the direction of arrow is telling that Cn is donating and Fe3 plus is accepting, and they will form a the hybridization will take place, D2 sp3. These 6 orbitals will hybridize, and then in these orbitals, see what happens. These 5 electrons which were present over here, they will first pair up like this. So the pairing has taken place, 2, 2 and 1. You know, maximum of 2 can be filled in one orbital. So 2, 2 and 1. Empty orbitals are these 6. Each of these empty orbitals will get one lone pair electron from Cn minus. Okay, and these empty orbitals will first hybridize to form D2sp3 through D2sp3 hybridization to form 6 D2sp3 hybridized orbitals. Then in each orbital a lone pair will be donated. Coordinate bond will be formed by Cn minus like this, and you get a complex FeCN6 3 minus. Okay. Now because there is one unpaired electron in this complex, so this complex is slightly paramagnetic. Alright, if unpaired electrons are present, then the complexes are paramagnetic. Let us take another example, formation of CONH3 whole 6 3 plus ion. Now this also involves D2sp3 hybridization. In this case, cobalt has atomic number 27. 27 in the ground state, you will see 2 of these are filled with 2 electrons, 3d orbitals, 3 are filled with a single electron, and here also 4s2 is there. Now when CO3 plus state, it will lose 2 electrons from 4s and 1 from here. So now you have, out of 3d, 1 is filled with 2 electrons. 3d out of 5 3d orbitals, 1 is filled with 2 electrons, and 4 3d orbitals are filled with single electron, and 4s is empty, 4p is also empty. Now in this, these will pair up and they will fill the 6 electrons which are there. They will get filled in these 3. That will leave 2 3d orbitals vacant. Then 1 4s is vacant and 3 4p are vacant. So the hybridization will take place, D2sp3 hybridization, and 6 D2sp3 hybrid orbitals will be formed. Each will get a lone pair from NH3, ammonia. Nitrogen has a lone pair, and they will form coordinate bond. So we will get a complex CONH3 whole 6 3 plus. Now there is no unpaired electron in this complex, so this complex will be paramagnetic. magnetic. All right. Sorry, diamagnetic. If there is unpaired electron present, it is paramagnetic. And because in this complex there is no unpaired electron, so this complex will be diamagnetic. Is it clear? Okay. So this is about D2sp3. Now let us, I've not shown you the diagram here, but let us just consider a case of sp3d2 hybridization. Like for example, COF6 3- ion. Now cobalt, you already know cobalt. Its electronic configuration is 4s2. Atomic number is 27. So electronic configuration, valence electrons will be 4s2 and 3d7. Alright. So CO3+ ion becomes, after removing 2 electrons from here and 1 from this, it becomes 3d6, and 4s and 4p are vacant. Alright. So now what will happen in COF6 3-, the hybridization that takes place is sp3d3. These will remain as such. They will not pair up like they did over here. You have 4s which is free, 4p is also free, and 4d is also vacant. So instead of these pairing up and leaving these two vacant, what is happening? The fluorine will F- will donate the lone pair to 4s, 4p and 2 of 4d. So that is the outer complex. Alright. So you get sp3d2 hybridization. 6 orbitals will be formed by sp3 and 4d, 2 of 4d. So sp3d2 and NH3 will donate coordinate bond, will form a coordinate bond with each one of these, and you will get a complex. And in this complex there will be unpaired electrons. These 4 are unpaired, so it will be a paramagnetic complex. So like this, outer orbital complex and inner orbital complex. Next, let's move on to tetrahedral complexes. In tetrahedral complexes, they are formed by sp3 hybridization. Okay, coordination number is 4. Now let us take an example. NiCO4. Oxidation state of nickel in this complex is 0, and it involves sp3 hybridization complex. If you look at nickel atom, atomic number is 28. So the electronic configuration becomes 4s2 and 3d8. Alright, so 3 of the 3d are filled with 2 electrons and 2 of them have 1 electron each. Oxidation state of nickel is 0. So what happens? This 2 of 4s, they come and pair up with the 3d, and 4s becomes empty and 4p also becomes empty. Now the 4s and 4p orbitals, they hybridize. So s and 3 of p. So sp3 hybridization takes place. They form 4 sp3 hybrid orbitals, and then the CO, which contains a lone pair, forms coordinate bond with each one of these 4 COs. Alright, so the complex is formed NiCO whole 4, and in this complex you can see each of the electron is orbital is filled with 2 electrons. All the electrons are paired. Alright, so what type of complex will it be? When all the electrons are paired, it is diamagnetic because there is no unpaired electron. Now let us take an example of another example. CuCl4. Now in CuCl4, copper has atomic number 29. So electronic configuration is 4s2 3d9. Okay. Now Cu2 plus will lose 2 electrons, so obviously those 2 electrons are lost from the 4s orbital. So here you have 3d9 and 4s is vacant and 4p is also empty. So hybridization takes place in 4s and 4p, sp3 hybridization, and in 4 sp3 hybrid orbitals are formed, and to each one Cl minus forms a coordinate bond and gives the lone pair. Sharing takes place like this. So a complex is formed, CuCl4 2 minus. Now in this complex there is one unpaired electron, so this complex will be paramagnetic in nature. Okay, so this is about the tetrahedral complexes in which sp3 hybridization takes place. Next we come to square planar complexes. Square planar complexes also have coordination number 4, but the type of hybridization that takes place is dsp2. Let us take an example. First example is of NiCN4 2 minus. Now in this complex ion, oxidation state of nickel is +2. See, nickel atom has atomic number 28, so electronic configuration 4s2 3d8. Alright, so Ni2 plus it loses 2 electrons of 4s, so you are left with 3d8. Now this S and the 4p, they hybridize to form 4. They do not hybridize like that. What happens is that these 2 electrons which are present in 3d, they pair up. So you have 4 3d orbitals filled with 2 electrons each, and one 3d orbital is vacant. So one d orbital, one s orbital and 2 of p orbital, they hybridize in the form of dsp2 hybridization, and 4 dsp2 hybrid orbitals are formed, to which each dsp2 hybrid orbital gets a lone pair from Cn minus. 4 Cn minus give 4 lone pairs and form 4 coordinate bonds with these dsp2 hybrid orbitals, and you get a complex NiCN4 2 minus. Now all the electrons in this complex are paired, so this complex is diamagnetic in nature. Next example, let us take CuNH3 whole 4 2 plus ion. Oxidation status of copper is 2 plus. See, the charge on the complex gives you this oxidation state because it is attached to neutral ligands. A copper atomic number is 29, that means 4s2 and 3d9. Alright, but copper exists because of the half filled and fully filled orbitals being more stable. Copper exists in as 3d10 4s1. So Cu2 plus ion mein one of the 4s will be lost and one of 3d will be lost. Alright, so Cu2 plus contains 3d9, 4s is available and 4p is also available for hybridization. Now in this case, CuNH3 whole 4, again the electron that is present here in 3d, it jumps to 4p, and d orbital, p orbital and s orbital, 2 of the p and s and d, they hybridize into dsp2 hybridization, and then one ammonia, each of the ammonia, 4 ammonia, they form coordinate bond and give a lone pair to these hybrid orbitals, and a square planar structure is formed of CuNH3 whole 4 2 plus. Okay, now it has been observed in X-ray studies that a square planar geometry is formed. So we have assumed that this 3D electron has jumped to 4p. Alright, vacant 4p. And the hybridization is dsp2 hybridization. And because of the presence of one unpaired electron, the complex is paramagnetic. Alright. So this is how you can predict the magnetic quality, the geometry of the electron, the type of hybridization. Now we move on to limitations of valence bond theory. There were a few limitations. It gives only qualitative explanation for complexes. It does not make the exact prediction regarding tetrahedral or square planar structure of 4 coordinate complexes. It does not distinguish between weak and strong ligands. It does not explain detailed magnetic properties of complexes, and it fails to explain the absorption spectra given by the complexes. So these are the limitations of valence bond theory. Now next we come to factors affecting the stability of a complex. First factor is charge on central metal ion. Greater the charge density on central metal ion, greater is the stability of complex. Next is the size of metal ion. As the size of metal ion decreases, stability of complex also it will increase. The order of stability is CD2 plus has less stability compared to manganese, which has less stability compared to Fe2 plus, which is less than CO2 plus, which is less than Ni2 plus, which is less than Cu2 plus, which is less than Zn2 plus. This order is called Irving-Williams order of stability. Next is the nature of ligand. The more basic a ligand, greater is the stability of complex formed by it. Then for anionic ligand, higher the charge, smaller the size, and more stable complexes form. Thus F minus gives more stable complexes compared to Cl minus. The chelating effect, complexes formed by chelating ligands are more stable than their monodentate ligands due to less strain in the chelate. Alright, now next is importance and applications of coordination compounds. Ni2 plus is detected by dimethyl glyoxim, which forms red color by forming complex. Presence of Fe2 plus can be detected by addition of potassium ferrocyanide solution, forming Prussian blue complex. Hardness of water can be estimated by titration with EDTA. Okay. The ions causing hardness, that is calcium ions and magnesium ions, form stable complexes with EDTA. Metal extraction and purification. Metals like silver and gold are extracted through conversion into soluble complexes from which pure metal is obtained. Impure nickel is purified by converting it to nickel carbonyl and then decomposing. Ziegler-Natta catalyst is used in formation of polythene. Wilkinson catalyst is used in hydrogenation of alkenes. So coordination compounds, they are used as catalysts. Then for electroplating, silver, gold, copper, etc. metals are electroplated from their coordination compounds, which deliver the metal ions in a controlled manner. Coordination compounds also have biological importance. Chlorophyll present in plants is complex of magnesium. Hemoglobin in blood is complex of iron, while vitamin B12 is a complex of cobalt. Then they have certain medicinal uses also. Cis-PT NH3 2 Cl2 is called cisplatin. It is used in treatment of cancer. EDTA is used in lead poisoning. Excess of copper and iron are removed by chelating ligands. Deep penicillamine and desferrioxim B via the formation of coordination compounds. So these are the uses or applications of coordination compounds. This finishes your chapter. Revise what has been taught to you and try to solve the questions given in the book.